Okay, so our second speaker is Thijs Lahoven, and he'll be talking about progressive lattice sieving.
Yeah, thank you. Okay, so just to start easy with the talk, so what is a lattice? So I guess everyone knows, but okay, so we have some n-dimensional vector space here, and here in the center we have the origin. To get a lattice, we then take some independent basis vectors, say v1 and v2 in 2 dimensions, and in high dimensions you get v1 up to vn. And then you get a lattice by taking all integer linear combinations of these basis vectors. So you get an infinite grid of points, like all the gray points you can see there, and they are in a lattice, so like 1 times v1 minus 5 times v2, that's a lattice point. Okay, so that's a lattice, and this is a 2-dimensional lattice. Okay, so you can do lots of things with lattices, and one of the things you can do on lattices is solving hard problems, and one of the key hard problems on lattices is the shortest vector problem. So given some description of a lattice, so say given a basis of a lattice, find the shortest non-zero vector. So in this case, I mean, we have a 2-dimensional lattice, and we can just draw the lattice, and we can just see what are short distances, and we can just see that this vector S is the shortest lattice, shortest vector, and also minus S is the shortest vector. But okay, this is in 2 dimensions, and if you are using lattices, say for cryptography, then you are actually working in very high-dimensional lattices, and then you cannot just draw pictures and see what is the shortest vector, and then it's much harder to find like these shortest vectors. And so this is a central problem in lattice-based crypto to understand how hard exactly it is to solve the shortest vector problem in high dimensions, so in n dimensions. And so how this scales, how the complexity of this problem scales with the dimension n. And so people have been working on this for quite some time already. So this is roughly a theoretical overview of the asymptotic results related to the hardness of the shortest vector problem in high dimensions. And so all order terms are omitted here, and the log of the time and the space complexity is given here. So on the top row you can see enumeration, which has been around since the 80s, which has a super exponential time complexity, so like 2 to the order n log n complexity, or to the order n squared. But you can actually do better. You can solve SVP in dimension n in only 2 to the order n time. But then also you get this exponential space complexity, so that's all the other rows in the table. They are exponential time and exponential space. So asymptotically, for high dimensions, we know that this is certainly better than enumeration. The crossover point, that's a different story, of course. So all the bottom rows, they are somehow using some form of sieving, and okay, some are not exactly sieving, but you can also see them as sieving somehow. So you can see that the constant in the exponent has been decreased over the years quite a bit. So if you want a provable complexity, then the best you can currently do is 2 to the n time and 2 to the n space, which means that on any lattice you can prove that this algorithm succeeds in finding a shortest vector in 2 to the n plus small n time and space. But if you if you care more about average case behavior and you are not worried about making some natural assumptions to get better, more accurate estimates, then actually you can go much further down, and you can see that the best classical complexity is currently 2 to the 0.292 times n plus small n. And quantumly, if you do some kind of quantum searching, then you get to the 0.265 times n plus small n for the best quantum time complexity. And so all the bottom results, they are all based on sieving, and the top row is enumeration, and so theoretically we know that sieving is certainly better than enumeration in high dimensions. But actually, if you actually implement these algorithms like enumeration and sieving, then you see a very different picture. So here you have the result from the SVP challenge, where you can just download the lattice and try to solve SVP on this lattice. You can see that the best results for enumeration are currently in dimension 150. So some team of Japanese people, they solved the SVP challenge on a 150 dimensional lattice in like a few centuries on single core timings. And the best result with sieving is only in dimension 130. And that's also in ideal lattices, like on plane lattices, I think the best is like dimension 120 so far. So actually in practice, if you try to implement these algorithms, then enumeration is actually currently still better than sieving. So there the picture is reversed compared to the theory. Okay, so that's a bit annoying, like in theory one is better and in practice the other is better. So what do you actually want to do when you choose parameters for your crypto system? Because like if you do lattice-based crypto, then you somehow need to estimate the hardness of SVP for choosing your parameters. So for the NIST submissions, here's a rough overview of what they did to estimate the hardness of the SVP for choosing the parameters. So you can see that actually most of the submissions use Sieving for estimating the hardness of SVP. And most of them actually just discard the small n in the exponent and then just say like, okay, classically it takes like 2.292 n times time to solve SVP in dimension n. And only a few of them still base their estimates on enumeration. Okay, so it's not exactly clear where the crossover point lies, so it's not exactly clear which of them you should use. But you can see that most of them currently use Sieving instead of enumeration for choosing parameters. Okay, so just a rough overview of the first few slides. So it's a hard problem to understand how hard it is to solve the shortest factor problem in high dimensions. There are two main approaches at the moment, so enumeration and Sieving, which are really different because enumeration has a worse time complexity but has only like no memory at all, while Sieving has a better asymptotic time complexity but uses a lot of memory, which also makes it less practical because like if you want to use it with lots of gigabytes or terabytes of memory, then it starts to become a bit annoying. So theoretically we know that Sieving is certainly faster than enumeration in high dimensions, and in practice we know that enumeration is still better than Sieving in low dimensions, and the NIST submissions mostly base their estimates on Sieving. Okay, so even if you just say, okay, are we going to use Sieving for that, then still you would like to know, like, okay, we have the current best algorithms, but can we maybe still improve these algorithms? So can Sieving, for instance, still be improved? Or have we reached the limit of what we can do? So of course, that's I mean, I'm not going to say that this question will be answered very soon, but okay, theoretically, like if you look at asymptotics, I would say at the moment that it's probably not so easy to improve upon the 292 exponent, because like the techniques used for that exponent are actually, in a certain sense, optimal. I mean, they're not exactly known to be optimal in this application, but there is reason to believe that you cannot really improve upon this. And also some other techniques like tuple sieving have been tried, and also that doesn't work in decreasing the exponent. So probably theoretically you cannot really decrease this 292 exponent very quickly without any really new techniques that haven't been used so far. But in practice, actually, yes, you can still gain quite a lot by some smart tricks somehow. And then you don't really decrease like the 292 exponent, but still you might gain like a factor 100, 1000, whatever, and then maybe get sieving closer to enumeration in practice already, like in lower dimensions. And so that's the topic of this work. So that's a practical improvement to sieving. And also I should mention this work by Leo Ducasse from Eurocrypt this year, so that's in a few months. He also has some tweaks to really improve sieving in practice and actually getting sieving very close to enumeration already. So, I mean, people usually believe that sieving is not really competitive with enumeration in practice, but with these improvements, it's really getting much closer than before. Okay, so to explain this improvement from this paper, this progressive lattice sieving, I will first explain how sieving roughly works the standard way, and then how this progressive enhancement works. So standard sieving works as follows. So we have some lattice here, so we have the two-dimensional lattice again. What we first do is we just generate a bunch of random lattice vectors. So if we have a basis, then we can just take like integer linear combinations of these basis vectors. And that's a lattice vector, so we can quite easily generate quite long lattice vectors. So in this case, I have 10 lattice vectors here. And what we're going to do now is we're trying to combine these vectors to form shorter vectors. So we go through the list, through the vectors one by one. So V1, okay, we have one vector, there's nothing to do. Then we go to V2 and we check, okay, can we maybe add or subtract V1 from V2 to get a shorter vector? Well, in this case, that doesn't help us in getting shorter vectors. But actually, we can subtract V2 from V1, and that gives us a slightly shorter vector. I mean, this is slightly shorter, you have to believe me for that. Then V3, we can actually reduce it with V2 and V1 by adding V1 and adding V2, and then we get this much shorter vector already. Then we can also update V1 and V2 with this new vector V3. We can update V1 again with this V2 and V3. We can slightly update V3 again. And now actually we have two very nice, very short vectors in our lattice, V2 and V3, and all other vectors now will be reduced to the zero vector, because like we can really reduce it all the way to zero by just adding and subtracting V2 and V3. So all of them become the zero vector. And also in high dimensions, if you run this algorithm, then you will see that some reductions happen and you need more vectors at some point, and then again some reductions. Then at some point you will see a lot of collisions, like vectors being reduced to the all zero vector, like you see here, V10 being reduced to the zero vector. And if you see a lot of zero vectors, then probably your algorithm, or your list already contains the shortest vector. So in this case, V2, you can see that as shortest vector. And so that's roughly how sieving usually works. So you just generate a bunch of vectors and then you try to reduce them. And also, like the standard approach is to work in the full lattice from the start. You know, you just generate these vectors in the full lattice and then you try to reduce them. Okay, so the progressive extension of the Gauss sieve is improvements. It works slightly differently in the sense that it doesn't start from the full lattice right away, but it starts from lower rank sublattices. And that's a way to somehow make progress gradually and not try to solve the hard problem immediately, but start from easier problems and then expand from that. So how does it work? So if this is our base V1 and V2, then first we're going to only consider V1. So we have a sublattice generated by V1. So this is just these points on the line here. So that's a sublattice of the full lattice. And we're now going to do sieving basically in this sublattice. So we just generate a bunch of vectors from this sublattice. Then we're going to reduce them just as before. So we have V1, there's nothing to do. V2, then we can reduce V1 with V2. We can reduce V3 with V2. Okay, so we have one kind of short vector in this one-dimensional lattice. I mean, one-dimensional lattice is kind of simple. And then when we are done, done in this one-dimensional lattice, then we say, okay, we're going to extend our basis to two-dimensional lattice now, and we're going to use this vector that we found, or this list of vectors in general. We're going to use it for the next stage. So we found some vectors in this one-dimensional lattice, and we're going to use it as a preprocessed list for the next stage. And so in the two-dimensional lattice, instead of starting from scratch with no short vectors, now we start with this one short vector V0. And again, we do the same, but now we already have this short vector here. So we can reduce V1 with V0, V2 with V0. We can do some updates again, and then, okay, we find a lot of zero vectors again. So in two dimensions, you don't really see what happens in high dimensions, but you can imagine, like if you do sieving in, say, 70 dimensions, then what you would generally do, you just start from scratch and you generate all these vectors in this 70-dimensional space and you try to reduce them. And then actually it takes a lot of time before you actually start making progress. So you generate a lot of long vectors and you don't make a lot of progress. Well, with this progressive approach where you start from one-dimensional lattice and then a two-dimensional and three-dimensional, then actually you already start making progress quite quickly. And like before you reach the 70-dimensional lattice, you already generated this list of short vectors in this 69-dimensional sublattice of the full lattice. So when you reach the full lattice, you already have a list of very short vectors, which helps you a lot in reducing these new vectors that you find in this full lattice. So here in this case, we just have one vector that we got from this one-dimensional lattice. And if you go to higher dimensions, then you have a big list of short vectors that you can use for this new higher rank lattice. So this is mostly just a heuristic improvement. I mean, you can argue why this leads to improvements and how much roughly, but you can also just implement them. And here you have a rough overview of the improvements in some modular dimensional lattices. So the Gauss sieve and the pro-Gauss sieve, that's the algorithms I just explained. And the hash sieve and the pro-hash sieve, like the hash sieve is just a Niels-Neighbor extension, which is a bit faster than the Gauss sieve, also using a bit more memory. And the pro-hash sieve is also just a progressive extension of the hash sieve. And you can see that the progressive variants of these algorithms are quite a lot faster, like a factor of 30 or something in most dimensions. So, I mean, it's not an asymptotic improvement. You don't decrease the exponent, but still, you notice it quite a lot that you get these improvements. Okay, so just some idea of what is happening. Okay, so here, so the top figure, you can see the time per iteration, where an iteration consists of taking a vector and trying to reduce it with the other vectors. You can see that the number of iterations does not really change compared to just the original approach. but actually the time per iteration decreases quite a lot, because like if you already have a list of short vectors, when you go to a higher ranked lattice, then you can reduce the vector much faster than if you don't have this list to start with. And also the list size at the bottom, well, I mean, does not change too much, but you can also see that it's a lot smoother for the progressive variant. You get like almost a straight line compared to a bit of a wobbly behavior for the original approach. Also the rank, so like I said, so you start with one-dimensional sublattice, and then you go to a two-dimensional sublattice by just adding a new basis vector, three-dimensional, etc., all the way up to the full lattice, so in this case 70-dimensional lattice. So how does the rank scale over time? Well, you can see, yeah, you can also expect that the most work is done in the high rank lattice, in the full lattice. And so the low ranks you will go through it quite quickly, and then like most work is done between like ranks 60 and 70 basically. Well, you can see original sieving as doing progressive sieving, where you start at rank 70 basically. And also at the bottom figure, it's interesting to see that usually, if you keep track of the shortest vector that you found so far, so you have your list of vectors, you do some reductions, and then maybe you find some shorter vectors. So if you keep track of the shortest vector that you have in your list so far, then with original sieving, it usually takes a lot of time before you make any progress at all, because at the beginning you're just generating a lot of vectors and making some reductions, but not making a lot of progress. Well, with progressive sieving, you already start making progress quite quickly. Like already after 1 million iterations, you already found a quite short vector. And so finding approximate solutions, approximate shortest vectors is also much faster with progressive sieving, which is also what you would expect, that you find approximate solutions faster than exact solutions. Okay, so just a few more numbers. So this is mostly about the effects of basis reduction. So, I mean, there were some weird things about sieving that should not happen. Like before in sieving, you would not notice so much the effect of basis reduction. Like if you start with an LL basis or a BKZ30 basis, like a much better basis of your lattice, you would not notice it too much in the performance of your algorithm. Like standard sieving, it takes like 1900 seconds with LL basis and 60,000 with BKZ30. It's like, okay, it's a bit less, but not so much less. And you would expect, like, for enumeration at least, you really notice this difference. Like if you start with a much better basis, enumeration is much faster. And for sieving, you don't notice it as much, but now you notice it a bit more with this progressive approach. And again, that's what you would expect, that you gain more from a nice basis. And also for approximate SOP, you really notice it much more, because not only because you can generate shorter vectors, but also because in these lower ranked lattices you will find shorter vectors already if you have a better basis. So your list will already contain short vectors quite quickly. Yeah, so just to conclude, so progressive lattice sieving, it's an extension of general sieving, where you use a recursive approach similar to, say, enumeration and also the Voronoi algorithm. I didn't mention it, but like most SOP algorithms use this recursive approach, and sieving didn't, and with progressive sieving you do, so that makes sense. You find approximate solutions much faster, also exact solutions. It benefits more from reduced basis, as you would expect, and which did not happen before as much. You get slightly better predictability, but like I said, so you don't really get a reduction in the constant exponent. You still have the 292 and the 265. But okay, you get quite a lot of speed up in practice. Okay, so that's it. So thank you for your attention.